Hey everybody, welcome to video 15-1. This is the first in our unit 6 here about circles. And we're going to be talking about central angles and inscribed angles in this section. So we've already done some vocabulary work, so you already know what a chord is here, a segment whose endpoints lie on a circle. So a central angle is basically made up of two radii coming out of the center, C, and it is an angle that is less than 180 degrees, as you can see there. And then the most important thing is to tell the difference between these two angles is where does the vertex lie. So the central angle, the vertex lies at the center, because central and center, and then an inscribed angle is a vertex that lies on the circle itself, so like outside on the circumference of the circle. And then the sides of an inscribed angle are chords, whereas the sides of a central angle are radii, so just to keep that straight. As we're looking at the diagrams here, you can see some examples of a central angle. So this ACD is a central angle, and then ABD is an inscribed angle. So we're going to talk about the relationships between the sizes of these angles in a little bit. This is all we're going to talk about on this page though, so you can go over to page 780 next. And on page 780 we want to talk about understanding arcs and arc measure here and explain one. It's just really important for you to understand how the notations of these are written. Okay, as we think about these different types of arcs and their measures, you need to know three different kinds of arcs: a minor, a major, and then a semicircle, which is basically the cutoff between minor and major. A minor arc, as you can see in the figure here, we've got pretty much the exact same diagram in these first two spots, but the arc that we're referring to is different. So in a minor arc, we're referring to arc AB, which is just this portion on the between 2 points. Notice the notation here. We have two letters, capital letters, because we have 2 points that it's between. But notice it's not a segment line at the top, it's a little arc over the top, so you need to make sure that you understand that notation. A minor arc is equal to the measure of the central angle, and then a major arc is going to be equal to 360 minus the measure of the central angle. So whatever this angle in the middle is, that's what the arc that it corresponds to is. And sometimes you will see this referred to as what's known as the intercepted arc, because if you think about an interception in like football, an interception cuts off the pass. So the intercepted arc is cut off by the two radii coming out from the center. So that's the intercepted arc. A minor arc's measure is the same as whatever the central angle is. However, the rest of the circle, because remember the whole circle is 360 degrees here. So if, for instance, we had on the major arc here, we're trying to find the measure of arc ADB. Notice there's 3 letters that describe the major arc, one more letter than minor, makes sense. But if we were trying to find the measure of arc ADB here, and we knew some information like that the central angle was 70 degrees, for instance, then we would know that the central angle on the outside here, the arc AB, is also 70 degrees, but out of the rest of it, we would need to do a 360 minus that. So that would be 290 degrees for the measure of arc ADB in this instance. And then just a really quick definition here, a semicircle is an arc whose endpoints are the endpoints of a diameter. It's half of a circle. And so its measure is half of the full 360 for the circle, which is 180. Moving on to the next page. As we talk about adjacent arcs, just like adjacent segments, they're going to be arcs that are going to share exactly 1 point, and so they're not overlapping. We have an arc addition postulate, just like the segment addition postulate. We wrote this down before as small plus small equals big, and I want you to keep that idea in mind. Non-overlapping arcs, if we add their measures together, it's going to be the same as the measure of the full longer arc piece. So keep that in mind as we go down here to example 1. A lot of writing here. I'm going to help you try to talk through it a little bit. If the measure of angle BCD is 18, so let's write that on the diagram. I'm going to zoom in a little bit on this diagram so that we can mark it up a little bit more. There we go. The measure of angle BCD is 18 degrees, so that's inside here. And then the measure of arc EF is 33 degrees, so that's out here. Determine the measure of arc ABD using the appropriate theorems and postulates. And we're told that lines AF and BE are lines that intersect at the center point C. So again, what we're being asked to find is how big is this arc here on the outside. So all we're going to do there is we're going to use some vertical angles, as you can see. If EF's arc is 33, then the measure of the central angle on the inside, ECF, is also 33. And then its vertical angle, which is ACB, is also 33. So if we've got 33 here plus 18 here, then we know we're going to have the sum using the the arc addition postulate, and so we're going to get a final answer of 51 degrees. Because remember, whatever that central angle is translates right out to the minor arc every single time. Let's look at part B. If the measure of arc JK is 27 degrees, we're going to determine the measure of arc NP here using the appropriate theorem and postulate. So, and again, we're told that we have two intersecting lines that go across these two concentric circles. So arc JK is 27. Let's write that on the diagram. So that's out here. And then the measure of angle JCK, the central angle, is 27. So that puts the other angle on the vertical angles there. The measure of angle MCN is also 27 by the vertical angles theorem. I'm just abbreviating. Then if we know that's 27, then we also know that the measure of angle MCP is 90 degrees because it's marked that way with our right angle. And then we also know that the measure of arc MNP is also 90 degrees. So if we use the arc addition postulate there, MNP, which again is this whole big angle here, if we know that's 90, and one little piece of it is 27 here, then the measure of just NP is going to be the measure of the the arc that goes from M to N to P, minus arc MN, which we know is 90, minus 27, and so we get a final answer of 63. On your next page, you want to make sure on this page you're working on your turn number 4 here using those same exact arc addition postulates and central angles and everything. Now we're going to talk about an inscribed angle. Make sure you've done your turn number 4 before we start this part. But now we're going to talk about an inscribed angle. And remember, the inscribed angle is the one where that vertex is right on the outside of the circle. So there's a theorem that we can look at called the inscribed angle theorem, and it says that the measure of angle ADB, which is the inscribed angle, is always equal to half the measure of its intercepted arc. So remember, there's that terminology again. So whatever from the vertex out here, whatever these chords that make up the central angle cut off, whatever this angle is on the outside, whatever that arc is on the outside, the angle is half of that measure. So there's two ways to think about that. We can write it as that the angle is 1/2 of the arc measure, the way that it's written here, or we can also, because sometimes we know we might be given the angle first and not the arc, so we could also say that the arc is 2 times the angle. You want to kind of make sure you know that relationship goes 2 different directions. So in example 2, and I'm on page 783 here, we're going to use the inscribed angle theorem to find inscribed angle measures. And we're going to go ahead and do that with the information given on the diagram being 18, that arc BE is equal to. So we're going to go ahead and pull that back and say that if this arc is 18, then the angle inscribed off of it is going to be half of that, so that's 9 degrees. And then we're also going to be able to say that if we have 2 times the angle, remember, is equal to the arc. So if we trace out from this inscribed angle EAD to its intercepted arc, which is ED, then we can say that we know that intercepted arc is 108 degrees, or twice 54. So if we want to know all these different arc measures here, we have DE, we just found that. We need BD, which remember is all the way from B through E to D, so all we're going to do is add those up. So BD is going to be 18 plus 108, or 126. So we've got that part taken care of. And then we also want to find the measures of the full angle BAD. So we know we've already got the little angle 9 here, plus the 54 that we knew. So just add those 2 pieces together, we get 63. So that takes care of angle DAB. And then if we next want the measure of angle ADE, notice that we have another inscribed angle, and that the arc that it is cut off of, or that it cuts off itself, is a semicircle. So it's just going to be half of that semicircle, or 90 degrees. And that is always true anytime we have an inscribed angle that comes off of a semicircle. So keep that in mind whenever you see that happening. For part B, we're going to do the same idea here. So determining these 4 different pieces of information from the diagram, arc WX, arc XZ, XWZ's angle, and WXZ's angle. So let's walk through this. By the inscribed angle theorem, if we know that the measure of arc X, the measure of angle XZW is 9 degrees, then we know that that is equal to half of the arc. So again, we're going to multiply the angle by 2 to get the arc, and so we get 18 degrees there. We're going to notice that WXZ is a semicircle, and so therefore its measure is 180 degrees. And so once we know that, by the arc addition postulate, the measure of arc WXZ, right here, is 180 degrees, which is this small piece plus this other larger piece here. So when we know, we can just do a subtraction there, so we know that the rest of it, arc XZ, is just going to be 162 degrees. Then, as we're looking at the inscribed angle theorem next, we know the angle that's inscribed off of the arc that we have there of 162. Notice, it's hard to see, so I'm going to zoom in on this diagram real quick. But do you see how this side right here is so close to the circle. There actually is an inscribed angle there that remember, we're trying to find the measure of angle WXZ, okay, and XWZ. So we need to use the inscribed angle theorem like we talked about. Getting back to that, oops, a little too small there. So half of, remember, we did 180 minus 18, and we got 162 out here. And so half of that translates back to that corner right there, which is our angle XWZ, so that's 81. We're also going to note that arc WYZ is a semicircle, and so the measure of that semicircle is 180 degrees. And so if we're finding our very last piece right here, WXZ is an inscribed angle off of a semicircle. So we have half of the measure of its intercepted arc, WYZ, which is half of 180, which means we have another right angle. Are we seeing a pattern here? Inscribed angle off of a semicircle is always going to be a right angle. Okay, let's move on. On the next page, this is page 784. You want to make sure that you are doing your turn number 7 here, using those ideas of inscribed angles and working through those calculations. Then we're going to skip over explain 3, except for at the very top of this page, this is a picture of what we've basically stumbled across in the last 2 examples, which is that if we have an inscribed angle off of a diameter here, so here's my inscribed angle, the chords are cutting off a semicircle, okay, and it's on a diameter, then it's always got to be a right angle because it's half of 180 degrees. So that takes us to the end of our lesson, you guys, and I'm going to go ahead and work on the evaluate next, and we'll see you in the next video.